Well, imagine for a moment, if you will, a universe that refuses to conform to our most deeply ingrained common sense. A universe where the very smallest constituents of reality, the fundamental building blocks from which everything you sense and feel is constructed, behave not just oddly, but in ways that seem utterly impossible, even frankly ludicrous to our everyday intuition. We're talking about something so profoundly strange, so utterly counterintuitive, that it forces us to reconsider the very nature of existence itself. Forget what you think you understand about how things move, how they exist, how they interact. Because what I'm about to describe, the simple, elegant, and yet utterly confounding double-slit experiment, cracks open that comfortable understanding and reveals a reality far more bizarre and beautiful than any of us could have possibly concocted in our wildest dreams. Picture this, if you can, a beam of solitary atoms launched from some source, heading directly towards a barrier. This barrier has two incredibly thin parallel slits cut into it. Now, in the world we inhabit, the world of macroscopic objects, of golf balls, of raindrops, of even the finest grains of sand, the laws of physics are clear, unambiguous, even comforting in their predictability. Each atom, much like a tiny grain of sand, would, you'd expect, choose one slit or the other. It would pass through, leaving a distinct mark on a screen placed behind the barrier. And if you let enough of these atoms pass, you'd perceive two clear, distinct piles of marks, corresponding precisely to the two slits. That would be the picture, wouldn't it? If the quantum realm, this subatomic stage, simply played by the same rules as our tables, our houses, our planets. But here's where reality, this exquisitely woven tapestry of existence, demonstrates something utterly, profoundly astonishing. Something that makes the mind truly, gaspingly, pause. The act of merely opening a second slit, of providing an alternative pathway, doesn't just add a new route for these tiny ephemeral entities. Oh no, it does something far, far more radical. It actively erases the traces of atoms in places where they confidently appeared when only one path was open. It's an inexplicable, paradoxical disappearance. And then it becomes even more tantalizing, even more mind-bending. Any attempt, any single, delicate, almost imperceptible attempt to perceive which of those two paths an atom chooses, immediately, almost vengefully, snaps the picture back to mundane predictability. Two distinct lines appear on the screen, as if the atom, caught in the act of its deepest secret, hastens to adopt the guise of an ordinary law-abiding particle. It's as though it's saying, "Oh, you're looking." Fine, I'll be boring then. But then, just as quickly, you remove that curious gaze, you switch off that all-seeing eye of the experimental detector, and once again, a complex multi-banded pattern emerges on the screen. An interference pattern. It's as if each atom, in some mystical, ethereal way, has divided itself, traversed both slits simultaneously, its wave-like nature splashing across two distinct paths, and then, reuniting, created this incredible ripple on the canvas of probabilities. This isn't a magician's trick, you know. This isn't some flight of fancy, some abstract conjuring of the imagination. This is the double-slit experiment, and it shatters the very foundations of our understanding of matter, of time, and indeed, of the act of observation itself. The explanation for this utterly incomprehensible behavior, this profound challenge to what we perceive as common sense, lies at the very heart of one of the most powerful, successful, and simultaneously, one of the most mysterious theories in the annals of human thought. Its very breath can be sensed in every transistor, in every laser beam, in our very understanding of why stars shine, and perhaps most profoundly why we exist at all. How can something so profoundly counterintuitive be so utterly, flawlessly correct? This theory, of course, is quantum mechanics. And it's not simply a collection of equations, it's the profound key to understanding the architecture of the universe at its most fundamental level. Without its astonishing insights, the technological landscape of the last several decades, the very bedrock of our modern lives, would appear utterly different, desolate and primitive. Think about it. The silicon chips that now form the nervous system of contemporary civilization, the lasers that pierce the darkness and even heal our flesh, these are all its direct offspring. The television screens that colour our living rooms, the computers that relentlessly expand the boundaries of our intellect, the microwave ovens that warm our food, the mobile phones that connect continents and bring the world to our fingertips. These everyday miracles, which we often lazily accept as simply given, owe their very existence, their very possibility, to this one extraordinary theory. Quantum mechanics, with astonishing, almost unnerving precision, predicts and explains the behavior of the tiniest building blocks of matter. Not just atoms, these tiny, miniature solar systems of the microcosmos, but also the subatomic particles from which they are composed, these elementary vortices of energy and mass. It grants us a deep, though certainly not always intuitively graspable, understanding of how these particles interact, how they weave themselves into intricate patterns, ultimately forming the macroscopic world that we perceive, that we can touch, and indeed, of which we are an integral part. And it's precisely here, at the junction of its incredible predictive power and our often stumbling inability to fully grasp its essence with our accustomed classical minds, that the great paradox truly blossoms. How can a scientific theory so triumphantly explain the countless hows and whys of the world's mechanisms, and yet simultaneously remain so deeply enigmatic, so provocatively strange? Well, for most practical physicists, those who daily juggle its formidable formulae and precise rules, this isn't perceived as an insurmountable problem. The theory simply works, you see, and it works flawlessly. It has unravelled the tangled knots of countless natural phenomena. Its mathematical apparatus is honed to a brilliant sheen, logical and brilliantly clear. And indeed, do we truly have the right to expect that nature, at the level of these unimaginably tiny, almost ghostly atoms, would behave in any remotely familiar, predictable way, when our everyday experience is so utterly limited to the world of people, of machines, of trees and houses? The essence, you realise, isn't that quantum mechanics somehow distorts or misrepresents nature. No, the truth is far more profound. It's that nature itself, in its deepest, most fundamental manifestations, behaves in an unusual, paradoxical, almost mischievous way. And if quantum mechanics provides us with the theoretical tools to comprehend everything that we observe, then we have no justifiable reason to blame nature, or indeed the theory, for our own intellectual imperfections, for the inherent limitations of our imagination, forged as it is in the familiar macroscopic world. Some physicists, it must be said, even display an overt impatience with those of their colleagues, who still strive to uncover a more vivid, more intuitively understandable interpretation of quantum reality. Their position is pragmatic to the extreme. Enough of this philosophizing, grab your tools, start calculating, predict the outcomes of experiments. The search for an absolute understanding of something that is, in principle, not amenable to experimental verification in the familiar sense. That's a fruitless waste of precious time, an intellectual luxury that a working scientist simply cannot afford. And it's true, the standard, or Copenhagen, interpretation of quantum mechanics, the very one taught to physics students for decades, has even established strict rules and conditions that scientists must adhere to regarding the information they extract from nature in each specific experiment. It can certainly feel excessively opaque, almost deliberately obscure, but it's crucial to grasp from the very outset. Quantum mechanics is fundamentally unlike any other theoretical concept ever devised by human genius throughout the entire sweep of scientific history, even after 2 decades spent immersing oneself in its embrace, attempting to fathom its deepest meaning, to truly come to terms with it. Well, it's perhaps impossible to ever fully reconcile oneself to it. There exist numerous interpretations, including the popular and somewhat cynical shut up and calculate approach, which allows many physicists to work incredibly effectively without being tormented by profound existential questions. But this narrative, this story we're embarking on, isn't solely about the philosophical depths and baffling paradoxes of quantum mechanics. No, it's also about its triumphs, about its countless applications in our daily lives, in the past, in the present, and most thrillingly of all in the future. We are about to set off on a truly breathtaking journey. From the misty peaks of philosophy and the dizzying abysses of subatomic particle physics, through theories of higher dimensions and hidden realities, to today's brightly illuminated technological world of lasers and microchips, and beyond, to an even more astonishing tomorrow, a world of quantum magic, where the very boundaries of the possible will be fundamentally rewritten. What if the very act of existing for an electron wasn't about being in one place, but about being everywhere at once? To truly sense this primordial strangeness again, we don't need complex mathematical derivations or cumbersome, expensive apparatus. No, it's enough to simply return to that very experiment with the two slits. It's so utterly straightforward in its setup, and yet so exquisitely beautiful in its capacity to lay bare the mysterious essence of quantum mechanics, that it serves as the perfect starting point, the ultimate portal into this bewildering world. It can feel like genuine sorcery, a magical performance staged by nature itself. But let me assure you, there's no sleight of hand here, no hidden mirrors or cunning secret mechanisms. A rational explanation, in the sense that we are accustomed to understanding that word, for the situation I'm describing, simply does not exist. When we direct a beam of light onto a screen punctuated by two narrow slits, a characteristic interference pattern appears on a second screen positioned behind it, a rhythmic alternation of bright and dark bands. This phenomenon is easily explained, you see, if we accept that light behaves as a wave. Light waves, passing simultaneously through both slits, much like ripples on water from two stones thrown in close proximity, scatter and superimpose upon each other. Where the crests of these waves coincide, they reinforce one another, creating a bright band. Where the crest of one wave meets the trough of another, they mutually cancel each other out, forming a dark band. This is classic wave optics, and here, seemingly, there are no profound mysteries, no unsettling enigmas. Now, let's conduct an analogous experiment, but this time, instead of light, we'll employ ordinary sand. Grains of sand, these tiny, tangible particles of matter, falling through two slits, quite predictably form two separate, distinctly defined heaps on the bottom screen. Each grain of sand, obediently following the laws of classical mechanics, passes either through one slit or through the other. No waves, no interference whatsoever. Everything is simple, comprehensible, and entirely familiar. And now, let us prepare ourselves for an encounter with the truly unknown, for onto the stage step the atoms. A specialized atomic gun, a precision instrument of the subatomic world, discharges a beam of atoms onto a screen with two exceedingly narrow slits, positioned very close to each other. The second screen is coated with a special luminescent layer, on which tiny, ephemeral flashes of light ignite wherever a single atom strikes it. Atoms are, without a shadow of a doubt, the smallest discrete particles of matter, and following the logic of our previous experiment with sand, they should behave in a similar fashion. So, we begin by opening only one slit. On the back screen, precisely behind that single slit, flashes of light begin to appear, their distribution somewhat scattered, a slight blurring, which we can attribute to some atoms perhaps grazing the edges of the slit and deflecting slightly. Now, for the truly culminating moment, we open the second slit. Our intuition, our deeply ingrained experience with the sand, dictates that we should perceive two separate groups of flashes, two clear, distinct patches of light. But reality, with a knowing, almost mocking smile, once again laughs at our expectations. Instead of two predictable spots, a full-fledged interference pattern emerges on the screen, identical to the one we observed in the experiment with light. The very brightest region of the screen, defying all logical expectation, is its absolute center, the precise location where, according to any particle theory, we would expect to experience absolutely no atoms at all. Perhaps you might wonder, the atoms, as they fly past each other, somehow secretly interact, colliding in a special synchronized manner, guiding one another and thereby creating this wave-like pattern. But even this compelling hypothesis collapses, crumbles into dust when the experiment is conducted under even stricter, more isolated conditions. The atoms are released from the gun one by one individually. The next atom is only discharged after the previous one has already left its solitary flash on the screen, completely eliminating any possibility of their interaction in flight. And what then do we perceive? The flashes gradually accumulate, and where they cluster particularly densely, slowly yet inexorably, those very same light and dark bands of the interference pattern manifest themselves. This pattern, this ghostly ripple, cannot possibly be the result of the collective behavior of many atoms. So what then is truly happening? What makes this result particularly striking, particularly bewildering, is the following observation. There are specific regions on the second screen where atoms reliably land when only one of the slits is open. It would be entirely logical to assume that by opening a second slit, we are providing the atoms with an additional route, and therefore increasing their chances of reaching these particular regions. However, when both slits are open, the atoms cease to arrive there altogether. This means that if an atom genuinely passes only through one slit, it must somehow, in some utterly unfathomable way, know whether the second slit is open and adjust its behavior accordingly. Each atom departs the gun as a tiny localized particle, and it strikes the second screen also as a particle, confirmed by that distinct individual flash. But in the interim, during the process of traversing the barrier with its two slits, something utterly mysterious happens to it, something that compels it to behave like an extended wave, a wave that is capable of dividing itself into two parts, of passing simultaneously through both slits, and then interfering with itself on the other side of the first screen. How else, one might demand, can we possibly explain how a single atom, a singular entity, is somehow aware of the existence of both slits? Can we truly ever know a quantum particle without fundamentally altering its very nature? Let us try to penetrate deeper into this enigma, to, as it were, peer into nature's sleeves. We'll install a super-sensitive atom detector directly behind one of the slits. This detector, like a vigilant guardian, will register every atom that passes through its particular aperture. The results are both predictable and simultaneously deeply puzzling. The detector occasionally triggers, recording the passage of a complete atom, never merely a part of it. Atoms that choose the path through the other, unobserved slit will continue to leave their flashes on the second screen. But here's the truly astonishing part. As soon as we begin to observe just one of the slits, the entire complex interference pattern on the back screen vanishes. In its place, only two bright, distinctly delineated spots of light appear, positioned precisely opposite each of the slits. Now the atoms behave exactly as we would have expected from particles, much like the grains of sand in our earlier classical experiment. It truly gives the impression that the atom behaves like a wave when left to its own devices, but the moment we attempt to trace its path, it immediately corrects itself and exhibits exclusively particle-like behavior. The atom seems to possess some uncanny foresight, as if it knows in advance that we've laid an ambush and are lying in wait for it at one of the slits, and therefore it cunningly remains in the form of a localized particle. Could it be perhaps that the mere presence of the massive detector somehow physically influences the behavior of the atoms? But even this explanation fails to withstand scrutiny, because the moment we simply switch off the detector, thereby depriving ourselves of the ability to know through which of the slits each particular atom passes, the interference pattern reappears on the second screen, as if by magic. The key factor, the truly defining element governing the atom's behavior, turns out to be the very fact of our observation, our very knowledge, or indeed our ignorance, of its chosen path. And this, believe it or not, is still not the limit of the strangeness. There exist what are known as delayed choice experiments, where the decision to observe is made at the very last possible moment. You can install a detector near one of the slits, but only switch it on after the atom has already passed through the screen with the slits, but before it has had time to actually reach the detector itself. We can precisely calculate the atom's flight time by controlling its initial energy. It would seem, at this point, that it's far too late for the atom to suddenly decide to behave like a localized particle that passed only through one of the slits, because it has already, presumably, propagated as a wave and traversed both. But lo and behold, even in such delayed choice experiments, when the decision to observe is made after the path choice event should have already occurred, the interference pattern still vanishes, giving way to two distinct spots. It's as if the past itself can be altered by a future decision. What then is this incredible phenomenon? Quantum mechanics, you see, offers a rigorous mathematical description of what we observe, but it steadfastly refuses to provide an intuitively comprehensible explanation for what is happening behind the scenes when we're not actively observing. Physicists have had to, with a heavy heart, concede there is no rational escape from this labyrinth of paradoxes, not in the familiar sense of the word. The strange entity, it turns out, is not the theory devised by humans, but nature itself, which at the microscopic level insists on such a capricious, almost irrational reality. The poet Robert Frost, in his famous poem, wrote, "Two roads diverged in a yellow wood, and sorry I could not travel both, and be one traveller, long I stood, and looked down one as far as I could." But quantum objects, these fundamental building blocks of the universe, behave in an utterly different manner. A single atom, encountering Frost's diverging paths, can unhesitatingly choose both routes simultaneously. Atoms do not fret over choices made, because they are capable of simultaneously exploring all possible options. They clearly follow the delightful advice of the great American baseball player Yogi Berra, who once remarked, "If you find a fork in the road, pick it up." This astonishing behaviour is a manifestation of a fundamental quantum phenomenon known as superposition. Could our universe right now be splitting into countless parallel realities with every single quantum event? To truly grasp this concept, to paint a vivid picture in your mind, imagine a skier who needs to navigate around a tree standing squarely in their path. In our macroscopic world of trees and skiers, that individual would choose either the left or the right route. But in the quantum world, this skier could quite literally circumvent the tree from both sides at once. And this, you see, isn't just a rather beautiful metaphor. In the quantum world, such things genuinely, demonstrably occur. Professors Markus Arndt and Anton Zeilinger from the University of Vienna conducted what has now become a classic experiment using fullerenes, large carbon molecules composed of 60 or 70 atoms, C60 and C70, shaped rather like miniature footballs and having a diameter no larger than 1/1,000,000th of a millimetre. Despite their relatively substantial size by atomic standards, these molecules represent to date the largest objects for which the wave-like nature of matter has been convincingly demonstrated. When a beam of such fullerenes was passed through a diffraction grating with several slits, regions appeared on the detecting screen where the molecules simply did not land at all. Astonishingly, opening additional apertures in the barrier, instead of the expected increase in the number of registered particles in certain locations, actually led to a decrease. Such behaviour is absolutely illogical for classical particles travelling along definite trajectories, but it is in complete agreement with a model based on the wave nature of individual molecules. The detector registered individual clicks, corresponding to the arrival of localised molecules, but as data accumulated on the screen, a complex wave-like interference pattern gradually emerged, clearly indicating that each single molecule had simultaneously explored all available paths. So, from where then did this astonishing, this intuition-defying science truly spring? There's a prevalent myth, you know, that at the close of the 19th century, physicists, brimming with a rather self-satisfied confidence, believed that the majestic edifice of physics was essentially complete, that all fundamental laws had been discovered, and that only a few minor details remained to be tidied up. In reality, by the end of the 19th century, physics had accumulated such a colossal number of unresolved questions and unexplained phenomena that the atmosphere was, quite literally, crackling with the anticipation of a profound breakthrough. Scientists couldn't even reach a consensus on such fundamental questions as whether matter was composed of indivisible atoms or if it was continuous and infinitely divisible. Fierce debates raged over the applicability of Newton's mechanics to Maxwell's recently formulated theory of electromagnetism. Phenomena such as the photoelectric effect, the radiation from a perfect black body, the enigmatic line spectra of light emitted by various elements all impatiently awaited their explanation. The world was abuzz, indeed truly electrified, by the discoveries of mysterious X-rays in the year 1895, radioactivity in 1896, and finally the electron in 1897. Physics then found itself in a state of glorious creative chaos, poised on the very precipice of momentous change. A second myth asserts that the German physicist Max Planck in the year 1900 instantly wrought a revolution by proposing his famous formula to describe blackbody radiation, and that quantum theory was immediately born in all its dazzling brilliance. The reality, I assure you, was far more complex, far more dramatic, far more human. Quantum mechanics did not spring forth from the sudden illumination of a single genius. Its development spanned almost 3 turbulent decades and demanded the collaborative efforts of the greatest minds of that era from across the entire globe. Planck, striving to resolve a long-standing problem concerning how heated objects radiate heat, the blackbody radiation problem as it was known, was compelled to make a truly radical assumption, that energy is not radiated and absorbed continuously, but rather in discrete packets, which he termed quanta. Planck himself, initially, regarded his idea more as a convenient mathematical trick, a computational workaround rather than a profound, fundamental truth about the ultimate structure of the world, and indeed, he didn't immediately grasp the full depth and revolutionary implications of his own discovery. The energy of a single quantum of light, according to Planck, is directly proportional to its frequency, and the constant of proportionality, well, that's the famous Planck's constant, denoted by the letter Ah, and approximately equal to 6.63 times 10 to the minus 34 joule-seconds. This number, however infinitesimally small it may seem, is one of the truly fundamental constants of nature. If Planck's constant were, hypothetically, to equal 0, then no quantum behaviour, with all its inherent strangeness and wonders, would simply exist. The blackbody radiation problem resided in the perplexing fact that classical theories simply could not correctly describe the spectrum of this radiation. Wien's formula worked well for short wavelengths, but failed catastrophically at long ones. Lord Rayleigh's theory, conversely, accurately described the long wavelength part of the spectrum, but predicted what became known as the ultraviolet catastrophe, an infinitely large radiation power at very short wavelengths, which was clearly dramatically contradicted by experiment. Planck, striving to find a theoretical basis for Wien's empirical formula, and drawing upon the statistical methods of Ludwig Boltzmann concerning the behaviour of atomic oscillators, on the 14th of December 1900, at a meeting of the Berlin Physical Society, presented his revolutionary formula. He proposed that these hypothetical oscillators within the black body could emit or absorb energy only in discrete portions, proportional to their oscillation frequency. That is, energy was quantized. This was a radical departure from the then accepted theory of electromagnetism by Maxwell, within whose framework energy was considered a continuous quantity. It is crucial to note that Planck at the time did not assert that all energy in the universe consisted of quanta. He merely suggested that the process of radiation by a black body occurred in packets. For the idea of energy quanta to extend to light itself, it would require the audacious genius of Albert Einstein. In his miraculous year, 1905, Albert Einstein, then still a young and utterly unknown clerk in the Swiss Patent Office, published a series of papers, each one of which could have immortalized his name. Alongside his special theory of relativity and his work explaining Brownian motion, thereby definitively proving the existence of atoms, Einstein presented a revolutionary explanation for the photoelectric effect. This effect, which involved electrons being ejected from the surface of a metal plate when it was illuminated by light, also completely stumped classical physics. 3 key peculiarities were observed. Firstly, the energy of the emitted electrons did not depend on the brightness, intensity of the incident light, but rather on its frequency, or wavelength. Secondly, there existed a certain minimum threshold frequency of light, below which no electrons were emitted, regardless of how high the light's intensity was. And thirdly, there was no observable time delay whatsoever between the commencement of illumination and the emission of electrons. They were emitted almost instantaneously. Einstein, boldly extending Planck's nascent idea, proposed that light itself consists of discrete packets of energy, quanta, which later came to be called photons. According to his theory, each electron is knocked off the metal surface by a single solitary photon. The energy of this photon, in accordance with Planck's formula, depends on its frequency, which immediately explained the first peculiarity of the photoelectric effect. The threshold frequency corresponded to the minimum energy of a photon sufficient to tear an electron from the metal, explaining the second peculiarity, and the instantaneous nature of the effect was explained by the fact that the electron did not have to accumulate energy from a continuous light wave. Instead, it received all the necessary energy in one fell swoop, as a result of a collision with one single photon. It was for this work, and not for the theory of relativity, that Einstein was awarded the Nobel Prize in Physics in 1921. And yet, amidst all this profound strangeness, lies the very bedrock of our technological age, hinting at a future we can barely begin to imagine. Thus, a truly paradoxical situation emerged. Young's double-slit experiment convincingly demonstrated that light behaves as a wave, while the photoelectric effect irrefutably proved that light consists of particles, these tiny packets of energy we call photons. This inherent dualism, where the very same entity exhibits both wave-like and particle-like properties, became one of the central enigmas and a fundamental defining characteristic of the quantum world. The next significant stride in the development of quantum theory was taken by the brilliant young Danish physicist Niels Bohr. In 1912, he travelled to Manchester to work under the guidance of Ernest Rutherford, who had, not long before, proposed his planetary model of the atom, a tiny, dense, positively charged nucleus at the centre, with negatively charged electrons orbiting around it. However, this model, while intuitively appealing and easy to visualize, suffered from a serious internal contradiction. According to classical electrodynamics, an electron orbiting a nucleus should continuously emit electromagnetic waves, constantly losing energy, and consequently spiral inwards and very quickly, in approximately 1/1000th of a second, crash into the nucleus. Atoms, therefore, should have been inherently unstable, which clearly and dramatically contradicted the very reality of a stable, enduring universe. Bohr, inspired by the groundbreaking ideas of Planck and Einstein concerning the quantization of energy, proposed that the energy of electrons within atoms was also quantized. This meant that electrons could not exist in just any arbitrary orbits, but only in strictly defined stationary orbits, each corresponding to its own discrete energy level. An electron could only jump from one stationary orbit to another by either emitting or absorbing a photon, the energy of which would be precisely equal to the difference in energy between those two orbits. This Bohr model brilliantly explained the stability of the atom and the origin of the enigmatic line spectra, that unique set of discrete frequencies of light emitted or absorbed by each chemical element. However, despite its triumphs and initial successes, Bohr's model was applicable only to the simplest atom, hydrogen, and hydrogen-like ions, and could not explain the properties of more complex atoms. For that, a further, more profound development of quantum theory was urgently required, and that development, thankfully, was not long in coming. In 1924, a young French aristocrat, Prince Louis de Broglie, in his doctoral dissertation, put forth a daring and elegantly simple hypothesis. If light, which had traditionally been regarded as a wave, could, under certain circumstances, behave as a stream of particles, photons, then perhaps conversely particles of matter, such as electrons, could in turn exhibit wave-like properties. De Broglie proposed that every material object could be associated with a certain matter wave, the length of which would be inversely proportional to its momentum, and consequently to its mass and velocity. The more massive and faster the particle, the shorter the wavelength associated with it. For macroscopic objects, the ones we encounter in our everyday lives, ourselves, a car, a planet, these matter waves are so infinitesimally short that they are utterly impossible to detect. But for light particles, such as electrons, and even for entire atoms moving at relatively low speeds, de Broglie's wavelengths become sufficiently large that their wave-like properties can, in fact, manifest themselves in experiment. This, of course, immediately raised a tantalizing question. Could it be that this elusive matter wave, associated with the atom, somehow passes through both slits simultaneously in the famous double-slit experiment, while the atom particle itself passes through only one of them? If the universe itself is quantum mechanical, then where precisely does the measurement that collapses the wave function actually take place? In the classical Newtonian world, a profound determinism reigned supreme. Knowing the exact initial position and velocity of every single particle in the universe, as well as all the forces acting upon them, one could, at least theoretically, calculate its state at any future moment in time. The future, in essence, was utterly predetermined. However, even within classical physics, chaos theory subtly hinted that such a prediction would necessitate knowing the initial conditions with infinite precision, which is, in any practical sense, an impossible feat. The quantum revolution, however, brought with it an even more radical, a far more unsettling idea: fundamental indeterminism. The very concept of fate as a predetermined sequence of events was, at the scientific level, revealed to be profoundly flawed. In the quantum world, at its most fundamental layer, unpredictability reigns supreme, an unpredictability that is not linked to our ignorance or the imperfection of our measuring instruments. No, this is an inherent property of nature itself. We can only calculate the probabilities of various outcomes. A perfect, poignant example is the radioactive decay of atomic nuclei. Quantum mechanics allows us to precisely calculate the so-called half-life, the time it takes for half of a given sample of identical nuclei to decay, but it is, in principle, utterly incapable of predicting the exact moment when any particular, individual nucleus will decay. Knowing the half-life only makes sense when applied to a statistically large ensemble of identical nuclei. We can calculate the probability of a nucleus decaying over a certain period of time, but nothing more. Albert Einstein, until the very end of his life, simply could not reconcile himself with this probabilistic nature of quantum reality, which found expression in his famous plaintive phrase, "God does not play dice." However, as decades of subsequent research and meticulously designed experiments have unequivocally shown, in this particular debate, Einstein was, it seems, profoundly mistaken. In classical physics, the motion of objects is elegantly described by Newton's equations, which permit us to predict their trajectories with astonishing accuracy. However, in the micro world, these equations prove utterly useless, beautifully accurate yet fundamentally inapplicable. The Austrian physicist Erwin Schrödinger, expanding upon de Broglie's pioneering ideas about matter waves, in 1926 proposed a fundamental equation that describes not the motion of a particle as such, but rather the evolution in time of a certain mathematical entity, which he named the wave function, typically denoted by the Greek letters ESX, SEI. The solution to Schrödinger's equation for a specific quantum system, for instance an electron within an atom, is this wave function. It encapsulates within itself all possible information about the state of that given system. However, in stark contrast to classical quantities, the wave function itself does not provide us with a precise value for, let's say, the position of a particle in space at a particular moment in time. Instead, it only allows us to calculate the probability of finding the particle at this or that point in space, if we were to perform a corresponding measurement. To obtain this probability, one must square the amplitude or modulus of the wave function. Let's imagine an electron confined within a small box. At the initial moment in time, its wave function might be rather well localized in one of the corners of that box. But as time progresses, according to Schrödinger's equation, this wave function will inevitably spread out, blurring, expanding to fill the entire volume of the box. We would no longer be able to pinpoint the exact location of the electron, but we could determine regions where the probability of finding it is higher or lower. This situation can be vividly illustrated with an analogy involving the hunt for a burglar in a large city. The police might not know his precise whereabouts, but based on available intelligence, they can construct a probability map, indicating areas where he is most likely to be hiding or to commit his next crime. If the burglar is eventually apprehended at a specific address, that probability map immediately dramatically changes. Now he is precisely here and nowhere else. Similarly, if, as a result of a measurement, an electron is found at a certain point, its wave function instantaneously collapses, localizing itself to that very point, and the probability of finding it anywhere else becomes quite literally zero. And yet, amidst all this profound strangeness, lies the very bedrock of our technological age, hinting at a future we can barely begin to imagine. But what then truly happens to the electron when we are not perceiving it, when we are not performing a measurement? Most physicists who adhere to the standard Copenhagen interpretation of quantum mechanics believe that, in this scenario, the electron simply does not exist as a classical particle with a precisely defined position. Its state is entirely described by its wave function, which can be smeared out across space, existing in the form of a kind of potential cloud of possibilities. The moment we perform a measurement, the moment we look, or rather sense, this wave function collapses, and the electron materializes into one specific point. This concept, I readily admit, can seem utterly absurd, profoundly contradictory to our everyday common sense. The wave function, in order to describe phenomena such as interference, must intrinsically possess wave-like properties. Furthermore, it is a complex quantity, meaning that at each point in space, it is described not by one, but by two numbers, a real and an imaginary part. Each of these parts, in itself, represents a wave, and the complete wave function is their intricate combination, which lends it its complex, multifaceted structure. From the probabilistic nature of the wave function and its unique mathematical properties flows one of the most famous and fundamentally important consequences of quantum mechanics, Heisenberg's uncertainty principle. It states that we cannot simultaneously know, with arbitrarily high precision, the values of certain pairs of conjugate physical quantities for a quantum particle. The most well-known example of such a pair is a particle's position and its momentum, which is intimately linked to its velocity. Чем точнее мы измеряем положение частицы, тем менее определенным становится ее импульс, и наоборот. This isn't merely due to the imperfection of our measuring instruments, or the idea that the act of measurement itself inevitably disturbs the particle, though that too plays a role. No, the uncertainty principle is a fundamental property of nature itself, intrinsically woven into the mathematical structure of wave functions. If a particle's wave function is highly localized in coordinate space, implying a small uncertainty in its position, then its corresponding wave function in momentum space will be broadly smeared out, implying a large uncertainty in its momentum, and vice versa. Niels Bohr termed this phenomenon the principle of complementarity. Such seemingly mutually exclusive aspects as precise position and precise momentum are complementary and both necessary for a complete description of a quantum system. An example of the uncertainty principle manifesting in real systems can be found in so-called halo nuclei, where some neutrons or protons have a wave function that extends far beyond the main part of the nucleus, which is possible thanks to the very small uncertainty in their momentum. The period from 1925 to 1927 became a time of genuine revolution in quantum physics, a revolution far more profound even than that which Planck had initiated. Bohr's older quantum theory, despite its successes, could not adequately describe the spectra of atoms more complex than hydrogen, nor did it offer a deep understanding of the very nature of quantization itself. Young physicists, luminaries such as Werner Heisenberg, Max Born, and Pascual Jordan, developed an entirely new mathematical formalism, now known as matrix mechanics. It was founded upon representing physical quantities not by numbers, but by matrices, tables of numbers, and operated exclusively with those quantities that could, in principle, be observed in an experiment, deliberately eschewing concepts like electron orbits. Almost simultaneously and completely independently, the Austrian physicist Erwin Schrödinger, further developing Louis de Broglie's ideas about matter waves, proposed another mathematical approach, wave mechanics, the central element of which became his famous wave equation. It was soon demonstrated, notably by Paul Dirac and Wolfgang Pauli, that Heisenberg's matrix mechanics and Schrödinger's wave mechanics were, in fact, mathematically equivalent. They were simply two different, yet equally valid languages for describing the same underlying quantum reality. How then do these new, more profound ideas explain the fundamental strangeness of the quantum world? At the very core of all these explanations lies the concept of the wave function and its unique, almost mystical properties. One such property is the principle of superposition. It isn't exclusively quantum, you know. It's a general characteristic of any wave. Two waves on the surface of water, encountering each other, superimpose, combining to create a complex resultant pattern, which is their superposition. In precisely the same way, light waves passing through two slits interfere thanks to superposition. It turns out that the wave functions of quantum systems can also exist in a state of superposition. This means that a quantum system, for example, an electron, can simultaneously exist in several different states. An electron can be moving both quickly and slowly at the same time. It can be spinning both clockwise and anti-clockwise simultaneously. It can even, astonishingly, be in two or more different places at once. Of course, when we perform a measurement, we invariably find the electron in only one specific state, with one speed, one direction of spin in one particular place. However, the very possibility of existing in superposition prior to measurement is absolutely key to understanding quantum phenomena. That very interference pattern in the double-slit experiment, which arises even when atoms or electrons are passed through the slits one by one, is a direct consequence of the fact that the wave function of each particle passes through both slits simultaneously, existing in a superposition of two states, pass through the upper slit and pass through the lower slit, and these two parts of the wave function then interfere with each other. And yet, amidst all this profound strangeness, lies the very bedrock of our technological age, hinting at a future we can barely begin to imagine. When an atom emerges from the atomic gun, its wave function can initially be quite well localized in space. However, as it travels towards the screen with the slits, this wave function, according to Schrödinger's equation, inevitably propagates. It spreads out. Upon reaching the screen with the slits, this extended wave function divides into two parts, each of which passes through its respective slit. It's crucial to understand that we are describing here the evolution of a mathematical quantity, not the behavior of a classical particle. On the other side of the slits, these two parts of the wave function again propagate and superimpose upon each other, meaning they enter into a superposition and interfere. By the time this resultant wave function reaches the second detecting screen, the distribution of its amplitude, and therefore the square of its amplitude, which represents the probability of detection, is such that there are regions where the probability of an atom arriving is high, the bright interference fringes, and regions where it is close to zero, the dark fringes. Although each specific atom is registered on the screen at only one point, the statistical accumulation of many such arrivals from identically prepared atoms is what ultimately forms the observed interference pattern. The wave function, you see, isn't the atom itself. It's our most complete mathematical description of its behavior and its potential possibilities, especially during the time when we're not observing it. Even more vividly and astonishingly, the principle of superposition is demonstrated in devices called quantum interferometers. In such a device, a single particle, a photon, an electron, a neutron, or even an atom, upon entry is directed onto a so-called beam splitter, for example, a semi-transparent mirror for photons, which offers it the opportunity to choose one of two different spatial paths within the instrument. According to quantum mechanics, the particle's wave function splits and simultaneously follows both paths, even if these paths are physically separated by a significant distance, centimeters, meters, or theoretically even light years. These two paths are then brought back together and directed onto another beam splitter, after which detectors are placed. If the particle indeed traversed both paths simultaneously, then at the output, interference will be observed between the two parts of its wave function, which will lead to the particle being detected with a high probability in only one of the detectors and almost never in the other. However, if we attempt to determine which of the two internal paths the particle took by installing a detector on one of them, the interference pattern at the output immediately vanishes, and the particle will be detected with equal probability in both output detectors. Furthermore, sophisticated experiments have been conducted with a so-called quantum eraser, which have shown that the information about which path the particle took, which normally destroys interference, can be erased even after the particle has seemingly already made its choice, and in this case, the interference can be restored. It's as if the particle not only knows whether we are observing it now, but also anticipates whether we will try to erase that information in the future. Another astonishing and fundamental characteristic of the quantum world is non-locality, closely intertwined with the phenomenon known as quantum entanglement. Imagine, if you will, two hypothetical dice that always show the same result when rolled. For example, both land on 6, then both on 3, and so on. Even if one of them is on Earth and the other is on Pluto, and they are rolled simultaneously, accounting for the signal propagation time, such that they cannot communicate the result to each other. Such behavior would strongly hint at the existence of some instantaneous connection between them, seemingly violating the principle of the finite speed of light. In the quantum world, similar though more subtle correlations genuinely exist. If two or more quantum particles interact with each other in a specific way, their states can become entangled. This means they cease to be independent systems and are described by a single, unified, common wave function, even if they subsequently fly apart to an enormous distance. A measurement performed on one of the entangled particles, which determines its state, for example the direction of its spin, instantaneously, faster than the speed of light, determines the state of the other particle, regardless of the distance separating them. This phenomenon, known as the EPR paradox, named after Einstein, Podolsky and Rosen, who first described it in 1935, was termed spooky action at a distance by Einstein, and he considered it proof of the incompleteness of quantum mechanics. He posited that there must exist some hidden parameters that predetermine the measurement results for both particles in advance. However, in 1964, the Irish physicist John Bell derived a mathematical inequality, Bell's theorem, which demonstrated that if such local hidden parameters truly exist, then the degree of correlation between the measurement results for entangled particles cannot exceed a certain limit. Numerous experiments, starting with the pioneering work of Alain Aspect and his colleagues in 1982, have convincingly demonstrated the violation of Bell's inequalities, thereby confirming the reality of quantum non-locality and the untenable nature of theories based on local hidden parameters. Quantum mechanics is, indeed, profoundly non-local. There's even an astonishing idea of interaction-free measurements, based on quantum principles, a vivid example of which is the Elitzer-Vaidman bomb-testing thought experiment, or, in a more peaceful version, determining the authenticity of a diamond among fakes. Using a special type of interferometer, a Mach-Zehnder interferometer, one can construct a situation in which the presence or absence of an object, for example, a genuine photon-absorbing diamond, on one of the interferometer's paths influences the interference result, even if the photon that triggered the detector actually travelled along the other path and never directly interacted with that object. In some cases, you can confidently say that a diamond is real because it could have absorbed a photon if it had gone that way, without destroying it, as the registered photon entirely avoided any encounter with it. However, the deepest and still not fully resolved enigma of quantum mechanics remains the so-called measurement problem. Why do we never directly observe the wave function in the process of its evolution or superposition? Why does the very act of observation or measurement cause this wave function to instantaneously collapse into one of the possible definite states, with the choice of this specific state being inherently probabilistic? Why does the interference pattern in the double-slit experiment vanish the moment we try to ascertain through which particular slit an atom passed? This mysterious process, the collapse of the wave function, lies at the perplexing boundary between the quantum and classical worlds. The act of observation itself, even the most delicate, inevitably perturbs the quantum system. Heisenberg's gamma-ray microscope, a thought experiment in which the position of an electron is sought to be determined with the aid of a gamma-ray photon, vividly illustrates that the more precisely we want to know the position, the more strongly we change the electron's momentum. But this is only part of the story. Schrödinger's equation, which describes the evolution of the wave function, is strictly deterministic. Probability and randomness only enter the game at the moment of measurement, but where exactly does this elusive boundary lie between the quantum system, obeying Schrödinger's equation, and the classical measuring apparatus, which registers a definite result? After all, the measuring apparatus itself ultimately also consists of atoms and therefore must obey quantum laws. The famous thought experiment involving Schrödinger's cat lays bare the full acuity of this problem. A cat is placed in a sealed box along with a radioactive atom and a mechanism that, upon the atom's decay, releases a poison that kills the cat. As long as the box remains sealed, and we do not know whether the atom has decayed, it is, according to quantum mechanics, in a superposition of two states, decayed and not decayed. Since the cat's fate is rigidly linked, entangled, with the state of the atom, then the cat too must exist in a superposition of two states, alive and dead simultaneously. Naturally, the moment we open the box, we will discover either a live cat or a dead one. Never, ever, both at once. Proponents of the Copenhagen interpretation would argue that prior to the moment of measurement, opening the box, speaking of a definite state of the cat, whether it is alive or dead, is utterly meaningless. It exists only as a potential possibility, described by a wave function. But what if, instead of a cat, there were a human observer inside the box? Surely that person would know whether they were conscious or not, irrespective of whether anyone outside ever opened the box. And yet, amidst all this profound strangeness, lies the very bedrock of our technological age, hinting at a future we can barely begin to imagine. The measurement problem therefore truly splits into two key questions. Firstly, why do we never observe macroscopic objects, such as cats or measuring instruments, in a state of superposition of macroscopically distinct states, for instance, simultaneously alive and dead, or simultaneously registered a signal and did not register one? The answer to this question, at least a partial one, is provided by the concept of decoherence. When an isolated quantum system, for example a solitary atom in a superposition state, interacts, becomes entangled, with its macroscopic environment, which consists of an enormous number of particles, air molecules, atoms of the measuring apparatus and so on, this fragile quantum coherence, the ability to maintain superposition and interference, very quickly, almost instantaneously, leaks into the surrounding environment and is lost. The delicate superposition, as it were, dissolves into the vast number of degrees of freedom of the macroscopic medium, and we can no longer observe its explicit manifestations, such as interference. This process of decoherence is very real and has been experimentally confirmed in recent decades in experiments with mesoscopic systems, those existing at the boundary between the micro and macro worlds. For example, in the experiments conducted by Serge Haroche's group in Paris, where the superposition of states of an electromagnetic field, consisting of several photons, decohered in times on the order of a tenth of a millisecond. Decoherence explains why Schrödinger's cat, by the time the box is opened, will no longer be in a state of both alive and dead simultaneously. That state would be too rapidly destroyed due to interaction with the environment inside the box. However, decoherence does not solve the second, perhaps even deeper question of the measurement problem. Even if decoherence eliminates unphysical superpositions, leaving only classical alternatives, for example, cat is alive or cat is dead, how exactly is one single, observed outcome chosen from these remaining possible alternatives during a specific measurement? Why, in one instance, do we find a live cat, and in another, upon repeating the experiment, a dead one, if the probabilities of both outcomes were, say, 50-50? Quantum mechanics remains fundamentally probabilistic, and this unpredictability of the result of a single measurement simply does not disappear. There exists a multitude of diverse philosophical and scientific approaches to interpreting the profound meaning of quantum mechanics. The standard, or Copenhagen interpretation, primarily developed by Niels Bohr and Werner Heisenberg, is more of a pragmatic set of rules for performing calculations and correlating them with measurement results, rather than a full-fledged explanation of what is really happening. It does not answer the question of how exactly an atom passes through two slits simultaneously, but declares this very question meaningless, as it pertains to reality in the absence of measurement. It postulates the collapse of the wave function upon measurement, but does not explain the mechanism of this collapse. In contrast, the de Broglie-Bohm interpretation, also known as pilot wave theory or hidden variables theory, posits that quantum particles are always real, localized objects, moving along definite trajectories under the guidance of a real physical pilot wave, a quantum potential, that is associated with Schrödinger's wave function. In the double-slit experiment, the particle atom passes through one specific slit, but the pilot wave passes through both, creating the interference pattern that then influences the particle's trajectory. This theory is deterministic at a fundamental level, but appears unpredictable due to our principal inability to precisely know the initial conditions, the particle's position inside the wave packet. And it is explicitly non-local. A change in the wave function, and thus the quantum potential, at one point in space instantaneously affects it at all other points. A completely different approach is offered by Hugh Everett's many worlds interpretation. According to it, no collapse of the wave function ever occurs. Instead, every time a quantum system faces a choice, for example, an atom passes through slits, the entire universe, including the observer, splits into a multitude of parallel realities, in each of which one of the possible outcomes is realized. Schrödinger's cat turns out to be alive in one universe and dead in another. We, as observers, also split and become aware of ourselves only in one of these branching realities. There are other interpretations as well. The statistical interpretation, quantum mechanics only describes ensembles of systems, not individual events. The transactional interpretation, which posits an exchange of offer waves from the past into the future, and confirmation waves from the future into the past. The theory of consistent histories, and objective or dynamic reduction theories, which postulate a spontaneous measurement-independent collapse of the wave function. Despite these profound philosophical debates about the very nature of reality, quantum mechanics has exerted a revolutionary influence on our understanding of the structure of matter, and has led to truly incredible technological progress. Recall the dawn of the atomic age, which began with the discovery of mysterious rays. X-rays by Wilhelm Röntgen, radioactivity by Henri Becquerel and the Curies, and finally the electron by J.J. Thomson. Ernest Rutherford, with his groundbreaking alpha particle scattering experiments, discovered the atomic nucleus, and Niels Bohr was the first to apply early quantum ideas for explaining the stability of the atom and its spectrum. However, a truly deep and comprehensive understanding of atomic structure only came with the development of full-fledged quantum mechanics and the introduction of Schrödinger's wave function concept. It allowed for the explanation of the existence of electron clouds around the nucleus, the introduction of quantum numbers characterizing the states of electrons, and thereby the comprehension of the chemical properties of elements and the structure of Mendeleev's periodic table. Another purely quantum property, one entirely without analogue in the classical world, is the spin of elementary particles, a kind of intrinsic angular momentum. The spin of an electron, for example, can take on only two discrete values, up or down relative to a chosen direction, and explains such phenomena as the Zeeman effect, the splitting of atomic spectral lines in a magnetic field. Electrons, protons, neutrons, and their constituent quarks are fermions, particles with half-integer spin, which obey the fundamental Pauli exclusion principle. No two identical fermions can simultaneously occupy the same quantum state. This principle is a cornerstone of our understanding of atomic structure. It is precisely what forces electrons to occupy different energy shells, the stability of matter, and even the properties of such exotic objects as neutron stars. Force-carrying particles, such as photons, are bosons, particles with integer spin, and do not obey the Pauli principle. On the contrary, they love to occupy the same state, which forms the fundamental basis of how a laser works. Peering deep inside the atomic nucleus, physicists discovered that it is composed of protons and neutrons, collectively known as nucleons. These nucleons are held together by a powerful force called the strong nuclear interaction. The Japanese physicist Hideki Yukawa in 1935 proposed that this interaction is mediated by the exchange of special particles, pions. These pions are virtual particles. They are, as it were, borrowed from the vacuum for a very brief period, permissible by the uncertainty principle for energy and time. Delta U times delta T is greater than or equal to h bar over 2. And this borrowing of energy is possible thanks to Einstein's famous formula E equals m squared, which exquisitely links energy and mass. There is also the weak nuclear interaction, responsible for certain types of radioactive decay, such as beta decay, where a neutron in a nucleus can transform into a proton, or vice versa, emitting an electron, or its antiparticle, a positron, and an elusive particle called a neutrino. The phenomenon of quantum tunneling, where a particle can percolate through an energy barrier, even if its energy is insufficient to overcome it classically, plays a crucial role in alpha decay, the emission of an alpha particle from a nucleus, consisting of 2 protons and 2 neutrons, and, even more importantly, in the thermonuclear reactions that power our Sun and all the stars. Further investigations revealed that the nucleons themselves, protons and neutrons, are not elementary but are composed of even more fundamental particles, quarks. There are 6 flavors of quarks: up, down, strange, charm, bottom, and top, which possess fractional electric charges. In addition to electric charge, quarks carry another type of charge, playfully called color, conventionally red, blue, and green. The strong interaction between quarks, which binds them within nucleons, is described by quantum chromodynamics, QCD, and is mediated by the exchange of other force-carrying particles, gluons. Quarks, along with leptons, which include the electron, muon, tau lepton, and 3 types of neutrinos, constitute the so-called standard model of particle physics, an extraordinarily successful theory that describes all known elementary particles and 3 of the 4 fundamental interactions: electromagnetic, weak, and strong. The grand dream of theoretical physicists for many decades has been the creation of a unified theory, one that would harmoniously bring together all 4 fundamental interactions of nature. Quantum electrodynamics, QED, painstakingly developed by Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga, describes the electromagnetic interaction with incredible precision as the exchange of virtual photons, after a clever mathematical procedure called renormalization, which allowed them to elegantly dispose of infinities in calculations. In the late 1960s, Steven Weinberg, Abdus Salam, and Sheldon Glashow successfully united the electromagnetic and weak interactions into a single theory of electroweak interaction. The next step is the creation of the so-called Grand Unified Theories, GUTS, which attempt to incorporate the strong interaction into this scheme, often utilizing the concept of supersymmetry, positing that every known fermion particle has a supersymmetric boson partner, and vice versa. However, the most challenging and fundamental interaction, gravity, which in the macroscopic world is described by Einstein's general theory of relativity as the result of the curvature of space-time itself by mass and energy, has stubbornly resisted quantization and unification with the other forces. The search for a theory of everything, one that would harmoniously weave together quantum mechanics and general relativity, remains the holy grail of modern fundamental physics. Leading candidates for this role today are string theory, or its more modern iteration, M theory, which proposes that the fundamental objects are not point-like particles, but tiny one-dimensional vibrating strings, or multidimensional brains, existing in a space with more than 3 spatial dimensions, and loop quantum gravity, which attempts to quantize space-time itself, representing it as a discrete network of loops at the so-called Planck scale, the fundamental scale of length, time, and energy at which quantum effects of gravity are expected to become dominant. Beyond these profound fundamental quests, the practical applications of quantum mechanics continue to transform our world with accelerating speed. Recall the semiconductor technologies, founded on an exquisite understanding of the band structure of solid materials, the behavior of electrons in a crystalline silicon lattice doped with various impurities to create N-type and P-type materials, which led to the invention of the transistor, then integrated circuits, and finally, the ubiquitous microchips that power our computers and gadgets. Lasers, whose operation is based on the principle of stimulated emission of coherent photons by atoms in an excited state, have found applications in countless fields, from medicine and industry to consumer electronics and communication systems. The phenomenon of superconductivity, the complete disappearance of electrical resistance in certain materials at ultra-low temperatures, explained by the formation of Cooper pairs of electrons which behave like collective bosons, allows for the creation of incredibly powerful electromagnets utilized in medical tomography scanners, MRIs, and scientific particle accelerators. Nuclear energy, both the based on the fission reactions of heavy nuclei and the promising thermonuclear energy based on the fusion of light nuclei mimicking our sun, all represent a direct consequence of our deep understanding of quantum processes within atomic nuclei. In medicine, beyond MRI, which harnesses the phenomenon of nuclear magnetic resonance of atomic nuclear spins, positron emission tomography, PET scanners, is widely employed, using radioactive isotopes that emit positrons, the antiparticles of electrons. The annihilation of these positrons with electrons in body tissues generates gamma-ray quanta, which are then detected by sensors, allowing for the creation of images of organs' metabolic activity. Even such complex biological processes as genetic mutations might have quantum effects at their very core, for example, the tunneling of protons within the DNA molecule. The development of scanning tunneling microscopy, STM, and atomic force microscopy, AFM, has enabled us not only to perceive individual atoms on the surface of materials, but also to manipulate them, moving them with a sharp probe, which opens up fantastic prospects for nanotechnology, the creation of molecular machines and devices on an atomic scale. The recent discovery and investigation of Bose-Einstein condensates, macroscopic quantum states in which thousands or millions of ultracold boson atoms behave as a single coherent quantum wave, promises new breakthroughs, such as the creation of atom lasers, and this, is far from the limit. Experiments with single atoms and photons, cooled to ultra-low temperatures using lasers and held within special traps, allow scientists to directly explore and control such fundamental quantum phenomena as superposition, entanglement, and decoherence. These investigations have already led to the emergence of fields like quantum cryptography, which offers methods for encrypting information whose security is guaranteed not by the complexity of mathematical problems, as in classical cryptography, but by the fundamental laws of quantum physics, for example, the impossibility of measuring a quantum state without disturbing it, or the properties of entangled particles. If, one day, we succeed in building a full-scale quantum computer, it could unleash a genuine revolution across many fields. A quantum computer would operate not with classical bits, which can only be in a state of 0 or 1, but with qubits, quantum systems, for example, the spins of electrons or atomic nuclei, the polarization of photons, which, thanks to the principle of superposition, can simultaneously exist in states corresponding to both 0 and 1. By harnessing the phenomenon of entanglement to link multiple qubits, a quantum computer would be able to perform an enormous number of calculations in parallel, enabling it to solve problems that are, in principle, inaccessible to even the most powerful classical supercomputers. For example, quantum algorithms already exist, such as Shor's algorithm for factoring large numbers into prime factors, or Grover's algorithm for searching unsorted databases, that demonstrate exponential or quadratic speedups compared to their classical counterparts. The primary challenge on the path to creating a practical quantum computer is the relentless battle against decoherence, which relentlessly seeks to destroy fragile quantum superpositions and entangled states due to interaction with the surrounding environment. However, researchers are actively developing quantum error correction methods and searching for increasingly sophisticated ways to isolate qubits. And finally, quantum teleportation, a process that sounds like pure science fiction, but has already been experimentally demonstrated for individual photons and atoms. This is not the instantaneous relocation of matter through space, but rather the transfer of the complete quantum state of one particle to another, located elsewhere, using entanglement and a classical communication channel, with the original particle inevitably being destroyed, losing its original state, in the teleportation process. From the fundamental enigma of the two slits, which challenged our understanding of reality more than a century ago, to the astonishing prospects of quantum computers and teleportation, the quantum world continues to amaze, to inspire, and to promise new, even more incredible revolutions in science and technology. It remains strange, paradoxical, often counterintuitive, but it is the fundamental reality upon which our world is built, and our journey into its depths, our exploration of its boundless possibilities, has only just begun. The future, without any doubt whatsoever, belongs to the quantum,